The symbol for torque is a tau. It looks kind of like a T, only with a kind of a curly top, something like that. It's a Greek letter tau. In order to learn about torque, we actually have to go back a little bit and talk about two different types of motion. There is translational motion, and there is rotational motion. Visuals are always good, so let us start with a couple of visuals here. This is translational motion. This is rotational motion. And this is both at the same time. Force causes translational motion. Rotational motion is caused by a torque. In order to understand torque, we actually have to understand what force is. In order to understand what force is, we actually need to go all the way back and remember what mass is. Please remind me, what is mass? You've heard of mass? Yes, Mr. Baldwin. I remember something called mass. I love it when we get to review. Mass. Headley. It's something like that that's the important piece. It's a good approximation, but I need more. Crown.
Is it like the resistance to inertia or something?
It is a measure of inertia. Remember, mass is a measure of inertia. What is inertia? Mr. Lowe.
The ability to resist a change in movement.
A change in state of motion, the ability to resist an acceleration. So mass is a measure of how much ability something has to resist a change in state of motion or to resist an acceleration. Okay, let us remember what force is. In order to help you remember what force is, I will go through my demo, which, as you recall, looked like this. I have applied a force to our mass. Pooja, thank you. We have our mass, I apply a force. Please remind me, what is force? Rick.
The ability to cause an acceleration.
The ability to cause a change in state of motion of an object, or the ability to cause an acceleration. Great. So that was applying a force to Pooja and desk. Please observe me apply a torque to the wheel. I just did the same thing rotationally that I did to Pooja. So what is torque? What did I do to the wheel, Emily X? I spun it. Let's talk physics. Spun it. It's not very physicsy. Physics term. What did in physics terms, what did I do to the wheel? Mr. Chen.
Did you cause a change in angular acceleration?
I caused an angular acceleration, right? So I angularly accelerated the wheel. Notice the initial angular velocity of the wheel is 0. I cause an angular acceleration to the wheel. I can also do that by stopping it, right? Because it had an initial angular velocity, and I slowed that down. So torque is the ability of a force to cause a change in angular state of motion. Torque is the ability of a force to cause an angular acceleration. Class, the symbol for angular acceleration?
Fishy thing.
Fishy thing, also called?
Alpha.
Alpha. So, torque is the ability of a force to cause a change in angular state of motion or to cause an angular acceleration. Great. The equation for torque, tau is equal to FD sine theta, torque. F, where F is clearly the force that is causing the torque. D is called the lever arm. And the lever arm is the distance from the force to the axis of rotation. So D, the lever arm, is called the lever arm, is the distance from where the force is applied to the axis of rotation of the object. And theta, in this equation, is the angle between the force and the lever arm. Great. Now, I like to say that everything that you've learned about, everything you need to know about torque you already know, because you have approached and worked with, bless you, a door on many occasions. You have a natural ability to walk through a door. You've worked with them many, many times. As a child, you didn't understand how to use a door, and all sorts of different things happened, but through experimentation, you figured out how to open a door. For example, when you look at a door, generally, when you are approaching it, you look for the handle. The handle is located where relative to the axis of rotation?
Far away from it.
Perpendicular.
Where relative to the axis of rotation?
It's the furthest you can get away.
It's far away from the axis of rotation. When you approach a door, you push near the handle. Right? You don't approach a door and push right here to try to open the door. Ah. Why don't you push right next to the axis of rotation to open a door? Heather,
It takes more force.
say again?
It takes more force.
Why does it take more force?
Because, well,
Let's put a picture up. So we have our door. Our axis of rotation, in this particular case, the hinge, is right there. Normally, you are going to apply a force right there. My question is, why do we not apply a force right there instead? Dan?
Well, the farther away it is, the bigger D you have, and the more
D-
torque you can
D-
get. Lever arm,
The larger the lever arm, therefore,
the more torque you can
the
get.
more torque you can get for the same force applied, right? If I apply a force right next to the axis of rotation, we have a very small lever arm. Therefore, I must apply a very large force to get the same torque, to get the same ability to cause an angular acceleration of the object. In other words, if I apply a force close to the axis of rotation, I have to apply a larger force to get the same torque to open the door. You've learned that. Another thing that you will never do is push on a door like this to open it. In other words, you will not push like that. You will pretty much always push like that. Wow. Dana. Why would the angle of 90 degrees be best for you? Mr. Chen, help her out.
Because the sine of 90 degrees is 1, so, and then anything greater or less than 90 degrees will be less than 1. So
If you look at the curve for sine, right, it looks like this. At this point, we have 90 degrees. At any other angle, we're going to get some sort of value that is less than our maximum value for the sine of an angle, which is 1. So your best bet, in order to get the most torque with the same lever arm and the same force, is to apply a force at 90 degrees. If you apply a force at any other angle, for example, with this one, it would be some larger angle right here, something larger than 90 degrees, you're going to get a value for the sine of that angle which is less, and therefore you're going to get less torque. Great. You will also never try to open a door like this. Why not? You will never push like that on the door. Because, Mr. Lowe.
Because the angle would be 0,
And
that would give you a sine of 0 is 0, and then like would not be able to.
because there's no torque, right? I, in that particular case, was actually causing 0 torque. I was not trying to cause an angular acceleration. I was actually, in that particular case, trying to cause translational motion of the door through the hinge, which isn't going to happen, right? So please be aware of your angle and how that works. That. Dimensions on torque. Dimensions, please. Carlon.
We have newtons for force, and then for lever arms, meters. And that's it.
Right, because the sine of any angle is going to give you no dimensions. Class, a Newton meter is called
Joule.
a joule. So a Newton meter is called a joule. We do not call them joules. To identify them specifically as different than work and energy, we call it Newton meters, or in English dimensions, foot-pounds. It is Newton meters because torque is very different than work and energy. Torque is a vector. Work and energy are scalars. So again, it does have the same dimensions as work and energy, but it is different because it's a vector. Therefore, we identify it as different by calling it Newton meters. We do not call it